Hey everyone, let's talk about something we all run into code that's just too slow. You know, that clunky, sluggish feeling? Well, today we're going to unlock a secret weapon, a technique that can make your solutions super fast and clean. Let's dive right in. You know the feeling, right? You've got a loop inside another loop. And yeah, it works, but man, it feels heavy. If you throw a big data set at it, you could probably go make a sandwich and come back. That's what we call an O of n squared solution. And it's basically a big red flag telling us, hey, there's a much better way to do this. So what if you could solve these kinds of problems in just one pass through the data? No more nested loops, just one clean sweep. Sounds good, right? Well, that's exactly what the two-pointers technique lets you do. Okay, so how does this whole thing actually work? Let's get into the core idea. So the basic idea is pretty simple. You take two indices, we'll call them pointers, and you have them scan through your data, like an array, together. They're a team. Instead of that brute force method of comparing every single thing with every other thing, these two pointers work in a really smart, coordinated way to find the answer in a single pass. And this right here shows the difference perfectly. On the left, you've got the slow way, those nested loops, just checking every possible pair. It's a grind. But on the right, you see the fast way. It's so much cleaner. We're basically taking this huge, slow process and squashing it down into one quick, efficient scan. That's how you go from O of n squared to O of n. To really get a feel for this, let's think about a few analogies. For some problems, it's like you're squeezing a spring from both sides, with the pointers moving towards the middle. For others, imagine two runners on a track, one fast, one slow. If there's a loop, the fast one is guaranteed to lap the slow one eventually. And sometimes, it's like trying to find the biggest container you can make, or the shorter wall is always your limiting factor. All right, let's dive into the first big pattern, the opposite ends pointers. It's exactly what it sounds like. You put one pointer at the very beginning of an array or a string, and another one at the very end. Then you just move them towards each other. This is super, super useful, especially when you're working with sorted data. A classic example of this is the two-sum problem on a sorted array. The goal is to find two numbers that add up to a specific target. So you start with your pointers at the far left and far right. You add up the numbers they're pointing at. Is the sum too small? Well, you need a bigger number, so you scoot the left pointer to the right. Is the sum too big? You need a smaller number, so you scoot the right pointer to the left. You just keep doing that until you find your match. It's really that straightforward. And look at this. You can see how that simple logic translates directly into actual code. This go function is a perfect example. The structure is exactly what we just talked about. You set up your left and right pointers, you loop as long as they haven't crossed, you check the sum, and then you move one of the pointers. Clean and simple. But here's the million-dollar question. Why does this actually work? Why don't we miss the answer? It's all because the array is sorted. When we move that left pointer forward, we're not just getting rid of one number. We're getting rid of all the potential pairs it could have made with the right side. We're intelligently throwing away combinations that we know for a fact are too small. It's a guaranteed safe move. And this squeezing from the outside in idea pops up everywhere. Want to check if a word is a palindrome? Easy. Compare the first and last letters, then the second and second to last, and just keep moving inward. Reversing a string. Same idea, but you swap the characters as you go. Even trickier problems like threesome often use this exact same pattern as part of the solution. Okay, let's switch gears a bit. The next set of patterns isn't just about finding something. It's about modifying data right where it is or finding the absolute best value, like the biggest possible area you can create. This one's a famous interview question, container with most water. Imagine you have a bunch of vertical lines of different heights. You want to pick two of them to form the sides of a container that holds the most water possible. The key thing to realize is that the amount of water is always limited by the shorter of the two walls. So if you want any chance of finding a bigger area, the only logical move is to get rid of your current shortest wall and hope you find a taller one. And that's the whole secret right there. Think about it. If you move the pointer on the taller wall, your width gets smaller, but your height is still limited by that same short wall. So the area can only go down. The only way to potentially find a better, bigger area is to move the pointer from the shorter wall inward. This whole idea of a limiting factor is a recurring theme. You'll see it when you're removing duplicates from a sorted array where you have one pointer reading ahead and another right pointer that only moves when it sees a new, unique element. Or in the trapping rainwater problem, where the water you can trap is, you guessed it, limited by the smaller of the maximum walls to your left and right. All right, let's check out our final pattern, and this one's a little different. Forget about starting at opposite ends. What if both pointers start at the same place, but they move at different speeds? This is the fast-slow pointer pattern, and it is an absolute game changer for linked list problems. This is a classic, Floyd's cycle finding algorithm. You might know it as the tortoise and the hare. It's simple. You have a slow pointer that moves one node at a time, and you have a fast pointer that moves two nodes at a time. If that linked list has a cycle, like a circular track, the fast runner is guaranteed to eventually catch up and lap the slow runner. If there's no cycle, the fast pointer just runs off the end of the list. So, when do you use this? Two main situations. First, for detecting if a linked list has a cycle, and you can do it in O of n time with no extra memory, which is amazing. And second, it's perfect for finding the middle node of a list. By the time the fast pointer hits the very end, the slow pointer will be sitting right at the midpoint. Super handy. Okay, so we've looked at the three big two-pointer patterns. Let's wrap this all up with a quick and dirty guide, some key takeaways and common mistakes to avoid when you start using these yourself. All right, here are a few bite-sized tips to remember. First, if you get an array problem and it's not sorted, try sorting it. That's often the key that unlocks the two-pointer solution. Second, always figure out what the limiting factor is, like the shorter wall in the water container problem, and move that pointer. And finally, when you're working with linked lists and a fast pointer, always check that fast and fast.next aren't null before you try to move it. It'll save you a world of pain. And of course, here are the common traps to watch out for. Don't forget your edge cases, what happens if the array is empty or only has one element. Also, be super careful with your while loop conditions to avoid those classic off-by-one errors. And finally, if a problem asks for unique answers, like in threesome, make sure you add some logic to skip over any duplicate numbers so you don't get the same answer twice. And there you have it, the two-pointer technique. It's an awesome, super versatile pattern that can take your slow, brute force code and make it fast, clean, and elegant. So the next time you see a problem that involves finding pairs in an array or dealing with a linked list, you'll have this in your back pocket. Now the only question is, which problem are you going to go solve with it first?